In this segment, we're going to talk about the first law of thermodynamics applied to open systems. So, here's my first law. It says the change in energy stored by the system, and it can be stored three ways: internal energy, kinetic energy, and potential energy. That's equal to the net amount of energy transferred across the system boundary into the system. So that could be done by heat, by work, and if you've got an open system, by mass flow. So mass can carry with it a certain amount of energy, and so those last two terms account for that. Let's look at an open system. Here I've got mass coming into this box and it's going out of that box as well. And I may be interested in how the flow changes from the inlet to the outlet of that box. So let's look at our first law and kind of dissect the individual parts. That first term, the change in energy stored by the system, this is referring to the change in internal energy and kinetic energy and potential energy within the boundary of that system. The heat transfer, obviously that's the heat into or out of the system. The work, this is work effects that are associated with rotating shafts, so shaft work. This will be something that will come in contact when we talk about turbines and compressors and pumps. We could talk about boundary work, so you could have that as well in an open system, although we won't work any problems with that in this class, but just be aware that that would fall under that category. And you can have other effects as well. In this class, we'll primarily be talking about shaft work. All right, and then you've got those last two terms, so let's look at that. Well, this is referring to the energy, the mass coming in and out. So what I'm going to do is I'm just going to look at the mass coming in right now, but just be aware that this also applies to the mass going out. So I'm looking at a chunk of mass coming in, and I've drawn this kind of a big chunk here, but this is the energy of the mass that is crossing the system boundary right at that given time. And the energy or the mass that's coming in, it has energy in the form of internal energy, kinetic energy, potential energy, because it stores energy as well. And it also has the energy that's required to push it into that control volume. And then if you looked at the outlet, you would have energy required to remove it from the control volume. And this energy is called flow work. Sometimes you hear it referred to as flow energy, but it's the same thing. I say flow work, so just be aware of that. So let's look at that chunk of mass. So I've got a force being applied for it. In this case, it's pushing it into the system. And I could put that force in terms of pressure and the area that it's acting on. So it's acting on the surface area on that one face. And then it's moving it some distance L. And the reason that I define that is because work is a force acting through a distance. So I've got a force acting through some distance L, and now I'm going to put the force in terms of the pressure and the area. So PAL, your PAL, it's pressure, the area, times the length. And you'll notice that if I take that surface area and just multiply it by the length, well, this is a rectangle, so this is just the volume of that rectangle. So the flow work is equal to the pressure times the volume. And it's a capital W, so it's in terms of kilojoules, or if you're in English units, it would be in BTU. If you divided things through by mass and you put things in terms of, say, kilojoules per kilogram, then instead of being volume, you'd have a specific volume there. All right, so let's put things together. So the energy of the mass coming in and out, I may have multiple inlets and outlets, so I need to put a summation to account for that. So, and the mass coming in, for example, has 4 types of energy associated with it: internal energy, kinetic energy, potential energy, and flow work or flow energy. If I rearrange that and I put the internal energy and the flow energy or flow work terms beside each other, I notice that that's just the definition of enthalpy. So, all right, well, I'm almost ready. What I am going to do is I'm going to put things in terms of little h, little kinetic energy, little potential energy, intensive properties that would be useful for me if I needed to look things up in my tables, for example. All right, so now we're ready to put everything together. Here's my first law. And so I've got the change in energy stored within the system. I usually just lump all those 3: internal energy, kinetic energy, and potential energy associated with the system. We typically just lump all those together and just call that delta E. So it's delta E of the system. A lot of times you'll see the system subscript dropped. I'm going to do that in just a second, but it's the energy associated with the system. All right, now I'm going to take how I the equation that I've got for the energy of the mass coming in and out. I'm going to put that into my equation right there. And with an open system, you're often concerned with the rate at which things are being done. So if I divide through by delta T, I could put things in terms of the heat transfer rate, Q dot, the work rate or the power, which is W dot, and then instead of having a mass there, I've got the mass flow rate. And that's a lot more useful to me when I'm talking about open systems. And this right here is the equation that you're going to use most often when you're talking about open systems. Just kind of depends on what units you want it in, right? And just one last note, if you have a steady state process, which is most of the devices that we're going to analyze in this class, that dE dt is just going to be 0. And so that'll simplify your life a little bit more. So, all right. Well, thank you very much. And let me know if you have any questions.